So hello everybody. Yesterday we have started the new academic year, and today we restart after the summer break our series in lectures of functional analysis. So today our guest is Thomas Kalmes from Technical University from Chemnitz, and he will deliver a talk about the linear topological invariant omega for kernels of partial differential operators. So please.
Thank you, Adam. First of all, I would like to thank Adam and Krzysztof for the invitation to Poznan. It's a great pleasure to be here. And it's a great pleasure to give an offline talk after so many years of online talks. So I really enjoy seeing audience. Okay, the talk today, I would like to present some results which I have been working on for several years in one of the main research areas, and the most recent ones are obtained together with Andreas de Provere from University of Brussels. And before we get into things, just let me give you a brief outline of the talk. This will be divided into 4 parts. Of course, we start with an introduction, then we will have a look at Runge type theorems for certain non-elliptic partial differential operators. In the third part of the talk, we will study the linear topological invariant omega for kernels of partial differential operators, which I denote by EPX. The notation will be made more precise in a minute. And for reasons which will be presented in the introduction, we need this topological invariant with control. I will explain what this means in a minute. And once we have prepared all this, we will see in the fourth part of the talk quantitative Runge type approximation theorems for kernels of partial differential operators. Okay, let's start with the introduction. Most probably all of you know Runge's approximation theorem, which deals with the following question. You have 2 open subsets, x and y, of the complex plane, y contained in x. And then you consider holomorphic functions on y, and you want to approximate them by holomorphic functions on the larger set x in the compact open topology. So given an arbitrary compact subset k of y, we are looking for a holomorphic function g, holomorphic in x, such that the supremum norm over the compact set k of the difference of f and g is bounded by a given epsilon. And this is possible precisely when the complement of y in the complex plane does not have a compact connected component which is completely contained in the larger set x. Okay, put differently, this characterizes when the restriction map has dense range. In the 1950s, this approximation theorem has been generalized independently by Lux and Lagrange to the following setting. So the same equivalence holds if you replace the complex plane by RD, and if you replace holomorphic functions by the kernel of an elliptic partial differential operator with constant coefficients. So this is, you start with a polynomial. Here we use the usual multi-index notation. Such a polynomial of degree m, let's say, is called elliptic. The so-called principal part, which by definition is the part with only the highest powers, only has 0 as its real 0, only the origin as its real 0. And then you consider the kernel of this partial differential operator in the smooth functions. So we use Schwarz notation. So E of x is the space of smooth functions over x equipped with its standard pressure space structure. And then Lux and Lagrange proved that you can approximate 0 solutions to this elliptic equation on the small set y by 0 solutions of the same equation on the large set x, if and only if x does not contain a compact connected component of the complement of the small set. Examples of elliptic partial differential operators are the Cauchy-Riemann operator, then we obtain the Cauchy as kernel the holomorphic functions. So this is a generalization of this Runge approximation theorem, or for example, the Laplacian, and then we deal with harmonic functions. Okay, and we would like to know what can be proved, what kind of approximation theorem in this spirit can be proved if the polynomial P is not elliptic. So if there is a zero of the principal part, which is different from the origin. And before we attack this question, let's introduce some notation. Most of you are most probably familiar with this. So we equip the space of smooth functions with its standard locally convex topology, which is generated by the semi-norms indexed by a non-negative integer and a compact subset k of x. You take the supremum norm of all partial derivatives up to order a on this set k, and this subspace, the kernel of P, is of course equipped with the subspace topology. And in case we do not consider any partial derivatives, only the function itself, we simply write the norm with index k instead of k. Okay, we will also need the distributional kernel of the same partial differential operator, which we denote by d prime p of x. So these are the distributions on x, which satisfy this homogeneous partial differential equation in the distributional sense. And this will be equipped with the subspace topology of the distributions as the strong dual of the space of test functions, of compactly supported smooth functions, which we denote by d of x. I would like to recall the notion of hypoellipticity of a polynomial. A polynomial P is called hypoelliptic if every distributional zero solution in any open subset of Rd is in fact a smooth function, and then this distributional equation will hold classically, so this will be a pointwise differential equation. By the very definition of hypoellipticity, as vector spaces, the smooth kernel coincides with the distributional kernel, and it is a result of Lagrange, which says that they also coincide as locally convex spaces, so the topologies in fact coincide, which has as a consequence that the topology of the smooth kernel is in fact the compact open topology, if P is hypoelliptic. So examples of hypoelliptic polynomials are the elliptic ones, for example, the Cauchy-Riemann or the Laplace operator are hypoelliptic, but also the operator, the heat conduction operator is hypoelliptic but not elliptic. So for these examples, the space of smooth solutions is actually equipped with the compact open topology, and we are in the setting of the Runge theorem or Lax-Lagrange theorem when we consider EP of x. Okay, so our first objective is the following. Given two open subsets x and y in Rd, y contained in x, P non-elliptic, and we want to find conditions for when these restriction maps between the smooth kernels, respectively the distributional kernels, have dense range. And in the sequel, the letters x and y will always denote open subsets of Euclidean space. Okay, these kind of Runge approximation theorems, they have in recent years there have been some mathematicians being interested in this, in some kind of strengthening of this Runge approximation theorem, so-called quantitative Runge approximation theorems, which I would like to introduce now. And for this, let's introduce some more notation. For open subsets y and x of the Euclidean space, we denote this y doubly contained in x. This should be that y is a relatively compact set whose closure is contained in x, and this notation will only be used for open sets. So whenever you see this, the sets x and y are supposed to be open. Okay, so some years ago, Rüland and Salo proved the following quantitative Runge type approximation theorem, So we have bounded Lipschitz domains Z and X, Z relatively compact with closure contained in X, such that the complement of the closure of Z in X is connected, which implies that X does not contain a compact connected component of the complement of Z. So this is the topological or geometrical property which appeared in Runge and Lagrange. And then they considered certain second order uniformly elliptic operators on Sobolev spaces. So we have a matrix value, real and symmetric matrix valued functions with components in the Sobolev space W1 infinity, an infinity function C. And this operator should be uniformly elliptic plus some technical additional assumptions, which I do not want to present. And then they proved that for every bounded Lipschitz domain lying between Z and X, there is a constant C and S such that every solution to the homogeneous equation in the Sobolev space over Y to this operator can be approximated by a solution to the same equation on the large set X in the L2 norm over this closure of the smallest open set in this way. So they are closer than epsilon times the norm H1 norm of F on the intermediate space. And they also proved that the trace of this approximating function H on the boundary can be bounded above by polynomial term in the error approximation times the norm of the function to be approximated in Y. And they called this kind of approximation quantitative Runge approximation because they were able to show this additional upper bound which can be achieved. Okay, and our second objective is to generalize this kind of quantitative Runge approximation in the context of constant coefficient partial differential operators, so for the smooth kernels of constant coefficient partial differential operators, including elliptic ones. Okay, in order to outline the strategy of how to generalize this result to the desired setting, let's recall this property omega from the title of the talk. This is a property for Fréchet spaces. So these are locally convex spaces whose topology is given by an increasing sequence of seminorms, which should satisfy a certain property with a bunch of quantifiers. Don't look at the quantifiers. So what do we want to have? So given any G from our Fréchet space, we want to approximate it by another element H from the Fréchet space with respect to the kth semi-norm, governed by the lth semi-norm of the element we want to approximate. And the approximating element H, this should satisfy some growth condition, let's say, with respect to the nth semi-norm. This should be bounded by C over epsilon to S times the Lth norm of G. Now we want to approximate for an arbitrary K. So for every K, we wish to find some semi-norm L, which governs both the approximation and the growth of the approximating element with respect to an arbitrary semi-norm N. And of course, these constants C and S, they may depend on on the semi-norm M and L and K. Okay, so although this is a kind of decomposition property of the elements of an arbitrary element G, I would like to think of this as an internal approximation. So inside the given Fréchet space E, we want to approximate any G from E with another element from E with these properties. Okay, if we consider the special case, the special Fréchet space of the smooth kernels of the differential operators, then this property omega translates into this bunch of quantifiers. So here we have the supremum norm of all partial derivatives up to order k on the compact set k. This should be bounded. This approximation error should be bounded by the approximation threshold epsilon times the Lth semi-norm of the function g we want to approximate, and the approximating function h on an arbitrary compact set n with arbitrary partial derivatives up to order small m should be bounded by this threshold. Okay, this is quite technical, I admit, but this will play a role in the generalization of this quantitative Runge approximation. Of course, this pair L, so the compact set L and also the non-negative integer L, they will depend on the compact set K we choose in the first place and also the derivation order. And if we assume now that our restriction map between the smooth kernels has dense range, the approximating kernel, so the kernel over X, has property omega, and if it is possible that whenever we choose our compact set K as a subset of the smaller open set Y, if it is possible to choose this compact set L, this one here, which a priori sits inside X, if this even sits inside Y, then we can argue as follows, because we have dense range of the restriction map, then for this compact set L and the epsilon, the error approximating threshold epsilon over 3, we find some G, a homogeneous solution of the homogeneous equation in X, which approximates our homogeneous solution in Y with this here. Since L is a compact subset of Y, all this makes sense. And if now for this G, we choose an H according to property omega from 1 for the threshold epsilon over 3 instead of epsilon, ubiquitous triangle inequality will lead to this quantitative approximation. So we can approximate our function f, which is a homogeneous solution on the small set Y, by a homogeneous solution of the same equation on X with this approximation threshold times the Lth semi-norm of f. And the size of this approximating function on an arbitrary subset n up to an arbitrary order of partial derivatives can be bounded above by a constant over epsilon to the s times the Lth semi-norm of f. So this will then be a generalization, very vaguely, of this quantitative Runge approximation theorem. And of course, it will be very interesting to know the precise location of this compact subset L from Y in terms of the compact subset K, which we start with. Okay, and so as a part of our second objective, we want to establish the property omega with control, so controlling L once we know K, for the space, for the kernel of the partial differential operator on the large set X. Okay, so we have two objectives: generalize Runge type approximation theorems for non-elliptic operators, and the second one, establish omega with control for kernels of smooth kernels of these differential operators in order to establish this quantitative Runge approximation. Okay, let's start with Runge type approximation theorems for non-elliptic partial differential operators. So recall that our polynomial p giving the differential operator is not elliptic if there is some non-zero vector in Rd, which is a zero of the principal part of our polynomial. So this principal part is homogeneous of degree n. Okay, such a vector is called a characteristic vector for the polynomial p or for the differential operator. And since this principal part is homogeneous of degree m. Whenever we have such a characteristic vector, we can assume without loss of generality that it is a unit vector, and we may change the coordinates by orthogonal change of variables to assume that the first unit vector is characteristic for this polynomial P. Okay, moreover, we introduce the notation of P check of a polynomial, which is obtained by the polynomial P by multiplying the argument with minus 1 before plugging it into the polynomial. And then we see that psi is characteristic for P if and only if it is characteristic for P check. And the reason why we introduce this polynomial P check is the following. So we consider the transpose of our partial differential operator on the distributions. And this is given by the differential operator coming from the polynomial P check on the space of test functions. So we have this equality if we apply our partial differential operator to U, apply it to a test function V, then this is the same as applying the distribution U to the test function P check applied to the test function. Likewise, the transpose of the differential operator on the space of smooth functions is given by P check acting on the space of compactly supported distributions, which is denoted by E prime. So we have the same equality for the duality brackets as in the previous. Okay, so let's assume that E1 is non-characteristic for our polynomial, and we consider the hyperplane, which is given by the condition that the Euclidean scalar product with our characteristic vector is equal to 0. So the first component should be 0. And then suppose that the following additional hypothesis holds. So for every width of slab around this hyperplane, so minus epsilon times RD minus 1, so this is a slab of arbitrary narrow width around this hyperplane, we ask for the existence of a smooth solution to the homogeneous equation P check D of V is equal to 0, with the additional property that the slightly decreased slab is contained in the support of V. So the support is, of course, the complement of the largest open set where our function V is equal to 0. And the support should be contained in this narrow slab. And we ask that our function is real analytic in this slab minus epsilon half times minus 1. If this additional hypothesis holds, then we obtain the following necessary condition for dense range between the distributional zero solutions. So assume that this restriction map between the distributional zero solutions has dense range. Then there is no X, this should be RD, in RD such that the complement of our small set Y intersected with the translate by X of this hyperplane. So the first coordinate here is equal to this given X1. We take the intersection of these two sets, and then X does not contain any compact connected component of this intersection. So if you remember the condition of the Runge theorem, we did not have this intersection here. Here we have an operator P which has a characteristic vector, and if the restriction map has dense range, then a geometric property very similar to the Runge property holds. We only have to intersect here with arbitrary parallels of this hyperplane. Okay, if time permits, I will give a sketch of this proof at the end of the talk because it has a very nice geometric flavor. But for now, let's have a look at when this additional hypothesis 2 is satisfied. For this, we write our polynomial P as a polynomial in the variable psi d with coefficients being polynomials in the rest of the variables. So this is always possible. Since m is the degree of our polynomial p, the degree of these polynomials qj is bounded by n minus j. And now we assume that the last unit vector is not characteristic for a polynomial p, so it is not a zero of the principal part. Then it follows that this qn appearing here has to be a non-zero constant, otherwise ed would be a characteristic vector. Okay, and now assume that under the general condition assumption that E1 is a characteristic vector, ED is not. Then this additional hypothesis 2 holds if the degree of this polynomial's qj as a polynomial in the first variable is not only bounded by n minus j, but strictly less than n minus j for j between 0 and n minus 1, then one can construct such a real analytic zero solution like in this condition 2. So combining these two theorems, we now have necessary condition for dense range between the distributional zero solutions. For operators of first order, of course, we have to make a change of variables so that this non-zero vector in Rd is a multiple of Ed. It also applies to the heat conduction operator and to the free time-dependent Schrödinger operator, where E1 takes the role of the time variable, and of course Ed one of the spatial variables. Okay, so for these kind of operators, we now have a necessary condition for this dense range of the restriction. Additionally, we can apply these results to the following class of polynomials. We say that a polynomial P acts along a subspace W if the value of P only depends on the orthogonal projection onto the subspace W of a vector. And if for every non-zero vector xi from the subspace, the principal part does not vanish. So you can think of this as elliptic polynomials in less variables than D, then the subspace will be the first k variables, let's say, in Rd. Okay, and of course, we have to assume that our subspace is different from Rd to have a characteristic vector. Otherwise, the polynomial is elliptic and we don't have characteristic vectors. But in this case, we have Lax-Marchange theorem and we don't have to study anything at all. Okay, now let's look for sufficient conditions for this restriction maps to have dense range. For this, we recall that for locally convex spaces E and F and a continuous linear mapping operator R from E to F, this has dense range by the Hahn-Banach theorem if and only if its transpose is injective. Okay, here our spaces we encounter are the kernels of this partial differential operator on the large set X, which is the space E, respectively the smaller set Y, which is the space F, either in the smooth setting or in the distributional setting. And of course, R is the restriction map. Okay, so the spaces involved are the kernels of certain continuous linear operators. And the kernel of a continuous linear operator, the dual space of such a kernel is given by the quotient of the full space modulo the closure of the image of the transposed. Okay, so here our kernel is the kernel of a differential operator acting either on spaces of smooth functions or on spaces of distributions. So the dual space will be the space of compactly supported distributions or the space of test functions, so compactly supported smooth functions. And the transpose of the operator of our partial differential operator is this p-check. So the dual spaces are the quotients of E prime over Y modulo the closure of the image of p-check on the compactly supported distributions over Y, respectively. This quotient here for the space F, so the zero solutions on the small set, etc. Y replaced by X when we consider the space E here. Okay, so we have to check whether the transpose of this restriction map between these quotient spaces is injective. And here it is very inconvenient that the quotients are taken with respect to the closure of subsets. So this is a nightmare to deal with, and therefore we restrict ourselves to the case when these spaces here, which we quotient out, are closed already. And this is, luckily for us, this has been investigated by several mathematicians. Okay, so we are interested in when is this subspace here closed in the respective spaces. Let's consider item number 2 for the moment. So we deal with a non-zero partial differential operator on the space of smooth functions. So this partial differential operator always has dense range, which can be seen by convolving with a fundamental solution. So it is surjective if and only if the range is closed. So dense range plus closed range characterizes surjectivity. And by the closed range theorem, the range of this operator is closed if and only if the range of the transpose is closed. So this gives the equivalence between 2 and 3. And then Floret in the 70s showed that closeness of range of the transpose in the compactly supported distributions is equivalent to closeness of the range of the transpose in the test functions. So all these are equivalent, and we can apply characterization of Malgrange from the 1950s when such a non-zero partial differential operator is surjective. And this is the case precisely when the set X, which is involved, satisfies a property which is called p-convexity for supports, and which reads as follows. So you start with a compact subset K in X, and you consider all the compactly supported distributions U with the property that the support of transposed of P applied to U is contained in K. And all these compactly supported distributions should have their support in a fixed compact set L, which of course will depend on K. The reason why this property is called p-convexity for supports is that due to the theorem of supports, one can show that every convex set X is p-convex for supports for arbitrary non-zero polynomial, and that this p-convexity for supports property has some permanence properties like convex sets. So arbitrary intersections or the interior of arbitrary intersections will be p-convex for supports. Again. Okay, so convex sets are the good ones, and also elliptic operators are the good ones, because for elliptic operator, every open subset is p-convex for supports. So if you remember Lax-Malgrange, in this Lax-Malgrange setting, we always have closeness of the range, so we have always a good representation of the dual space of the zero solutions. Okay, and with this characterization of or with this equivalence of 2 and 3, Treff showed in the 1960s the following theorem, the equivalence of 1 and 3, and Wiechert in the 1980s added the equivalence of the second item, that our restriction maps have dense range in the setting that the large set X is p-convex for supports. Under the additional hypothesis that the small set is also p-convex for supports, if and only if every test function on the large set for which the support of p check applied to phi is contained in Y already has its support in Y. Okay, so this third item is the one we will use in the proofs, which I won't show, but this is our device for proving these commutative theorems. Okay, and the first one of these quite recently obtained together with Andreas. So we have a polynomial P which acts along a subspace and is elliptic there. Again, we have open subsets Y and X in the usual way contained in one another, for which the larger one is p-convex for supports. Then we have the following sufficient condition for denseness of the restriction maps that there is no X in Rd for which the larger set X contains a compact connected component of the complement of Y intersected with the translate of our subspace along which the polynomial acts elliptic by X. And then both restriction maps between the smooth solutions and the distributional solutions have dense range. And in case that the dimension of the Euclidean space is equal to 2, this sufficient condition is also necessary, which is also the case for elliptic operators, because then W is the whole space, and this geometric condition here is the same as in Lax-Malebranche. So X plus W is Rd. So the intersection here can be omitted, so that the condition reads X contains. There is no X such that the large set X contains a compact connected component of the complement of Y. Okay, so this theorem is applicable to first order operators as they act elliptically along one-dimensional subspaces. And this can be used to investigate kernels of differential operators which factor into first order operators, like the wave operator in one spatial variable. This is the product of two first order operators. And for this operator, we have this very strong approximation theorem, assuming that our small set Y is p-convex for supports. Then the restriction map from the smooth solutions over R2 of the wave equation restricted to this set Y has dense range, if and only if it is possible to find an open connected p-convex for supports superset X of Y such that the respective restriction map between the smooth kernels has dense range. And if this holds, we can even have a very strong form of approximation, because then every continuous function, which is a distributional solution of the wave equation in Y, for this, for an arbitrary compact set K, we can find a compactly supported continuous function G on R2, which on R2 is a distributional solution to the wave equation, such that G and F coincide in the neighborhood of K. So this is a very strong form of approximation, even at equality to the approximating function. And of course, we have a geometric characterization of those p-convex for supports sets Y for which this is possible. This is possible precisely when there is no X from R2, such that the complement of Y intersected with both diagonals translated by X does not have a compact connected component. Okay, so in particular, this is applicable whenever our small set Y, which is p-convex for supports, is assumed to be connected, because then in the second item we can choose X to be equal to Y, and for every connected set Y, which is p-convex for supports, we can apply this corollary. Okay, let's consider a second class of polynomials, respectively operators, where we have the characterization or a sufficient condition for this dense range property. Assume that our polynomial P is such that the principal part, the zeros of the principal part, is spanned by E1. So the zero set, since Pm is homogeneous of degree n, the zero set is always a cone. So with xi, every multiple of xi belongs to it. So effectively, this says that there is only one direction where the principal part vanishes. Okay, then assume that we have our open sets Y and X. The larger one should be p-convex for supports, and then we have the following sufficient condition for denseness of range. Again, the condition is that there is no X from Rd such that the larger set contains a compact connected component of the intersection of the complement of the small set with the translation by this vector X of this hyperplane where the first coordinate of the vectors is equal to 0. And then the restriction of self-dense range. And in case that our polynomial, ED is not a 0 of the principal part, so we can write it in this way with Qm being a non-zero constant, and recalling our necessary condition for dense range, that the degree of this polynomials as a polynomial in Xi1 is strictly less than the allowed upper bound m minus j, then this then this sufficient condition is also necessary. Okay, so the operators for which examples of operators for which such a representation holds, again, these are parabolic operators like the heat conduction operator or the time-dependent Schrödinger operator. So for these operators, we now have a characterization of the restriction maps between the respective solutions to the homogeneous equations for dense range. So usually when you consider problems where these operators show up, the domains where you consider functions, these are subsets of space-time. So we have a time interval times a space domain. And if this is the case here, so if y and x are of this form, then the restriction maps, they have dense range if and only if the space parts of this space-time domains satisfy the property which shows up in the Lax-Malebranche theorem, that the larger set does not contain a compact connected component of the complement of the smaller set. Okay, now let's come to the topological invariant omega. So now we have Runge-type approximation theorems. Now we want to have quantitative Runge-type approximation theorems with the aid of this property omega. And for this, I would like to recall where omega showed up, why this is important, and where it has been studied. For this, we recall the so-called problem of parameter dependence. So assume we have a surjective partial differential operator on the smooth functions over an open subset X of Rd. We know that this is characterized by the property of being p-convex for supports. And now we are given data for right-hand sides of our equation, which somehow depend on a parameter lambda, let's say regularly. And we are looking for solutions f lambda to the corresponding equations. And we ask that these solutions depend in the same way on the parameter lambda than the given data. Irregularity could mean continuous, smooth, real analytic, whatever. Okay, to give an abstract formulation of this parameter dependence problem, let's recall the epsilon product of Schwarz. For two locally convex spaces E and F, the epsilon product is defined as the space of continuous linear operators from the dual of E equipped with the topology of uniform convergence on the absolutely convex compact subsets into F. And for an operator T on E, we denote the epsilon product of T. We define the epsilon product of T with the identity on F, on the epsilon product of E and F by this formula. So what does this have to do with parameter dependence? So if our space F is a space of scalar valued functions on some set lambda, we may define E valued analog, which is the space of mappings from lambda to E with the property that for every element from the dual space composed with this F lambda, this should be contained in the scalar valued function space. And this is a good candidate for the E valued version of the scalar valued function space F lambda. And under mild assumptions on the spaces E and F lambda, it holds that this E valued version of the F functions is isomorphic to the epsilon product. And under this isomorphism, the epsilon product of T with the identity is given by this mapping. So we apply lambda-wise our operator T to the given data. And then the parameter dependence problem reads, if T is surjective in the first place, is the epsilon product of T with the identity on F lambda surjective again. Okay, so in the abstract formulation with the epsilon product, our initial question is the following: given a surjective operator on the smooth functions over X, for which locally convex spaces F is the epsilon product of the differential operator with the identity on F surjective again. And if F is, for example, the space of temperate distributions or the distributions over this open set lambda of Rd, this is the correct formulation of the parameter dependence problem. Due to a result of Grothendieck from the 1950s, we have here surjectivity if the space F is a Fréchet space. So, for example, continuous parameter dependence, holomorphic parameter dependence with respect to rapidly decreasing functions has a positive answer. Investigating this parameter dependence problem for dual spaces of Fréchet spaces, Vogt and Wagner introduced this condition omega. And because they showed the following, so given a surjective partial differential operator on the smooth functions, then its epsilon product with the identity of the dual space of the rapidly decreasing sequences is surjective if and only if the kernel of the partial differential operator has omega. So we have a positive answer to the parameter dependence problem where the second space is S prime. More generally, when the second space F is isomorphic to a product of Montel dF spaces for which the strong dual has a certain linear topological property called Tn. I don't want to go into details. So the third part here covers in particular F being S prime, so that we get a characterization of property omega for the kernel by the surjectivity of this epsilon product. Unfortunately, this epsilon product of Ex with S prime does not have a nice representation. So if you want to use this surjectivity here to characterize omega for the kernel of the differential operator, you have to find a different route than using a representation of this epsilon product. So when does the kernel have omega? In 1980, Petche showed that this is the case for convex sets and hypoelliptic operators. This is a quite technical proof which relies on the fundamental principle of Ehrenpreis for the representation of zero solutions on convex sets for partial differential equations. Vogt proved for arbitrary X and elliptic P, the kernel has omega, and his proof is even more technical and uses the representation of the dual space of the smooth solutions as a space of germs of real analytic functions in an abstract Hadamard three circles theorem. Okay, and we were interested in what can be said if X is not convex or P not a hypoelliptic, respectively elliptic operator. And as I mentioned, unfortunately, this epsilon product, okay, there is an X missing of Ex with S prime, does not have a nice representation to study the question, so we have to find some other route. And this is done by using some results provided by Bonnet and Domansky. And in order to explain how we use them, let's recall the result by Hermander, who characterized when our partial differential operator is surjective on the space of all distributions. This holds precisely when X is p-convex for supports, which is a property we already encountered, as well as p-convex for singular supports, which reads quite similar to p-convexity for supports. You only have to replace the supports by the singular supports, where the singular support of a distribution is the complement of the largest open set in its domain, where it is representable by a smooth function. Okay. Again, the notion p-convexity for singular supports stems from the fact that convex sets always have this property, and now the good operators are the hypoelliptic ones, which in particular contain the elliptic operators. And of course, one can ask the parameter dependence problem in the context of our partial differential operator on the space of distributions. This was thoroughly investigated by Bonnet and Tumansky. This started in the seminal work in 2006, and they gave the following answer to this question in an abstract manner. So we have a surjective operator on the distributions. Then the epsilon product with this operator with the identity on D prime is surjective if and only if the kernel, the distributional kernel, satisfies a linear topological invariant P omega. So this is a linear topological invariant for so-called PLS spaces, which is similar to the property omega. I don't want to give the definition. Only want to recall that Fréchet-Schwarz spaces are PLS spaces, and they have P omega if and only if they have omega. So in case we have a hypoelliptic operator here, then the kernel is the kernel in the smooth function. So it is a Fréchet-Schwarz space. Then this P omega is the property omega, which we already encountered. Okay, and if the kernel has P omega, then not only the epsilon product with the identity on D prime of R is again surjective, but again, we can have here as the space F, the space which is isomorphic to an arbitrary product of Montel DF spaces for which the dual spaces have Dn. Examples of these are S prime, D prime on R. And now we are lucky because by the Schwarz kernel theorem, this epsilon product has a very nice representation. It is the space of distributions on X times R. And under this isomorphism, the epsilon product of our differential operator with the identity is this partial differential operator, which is the so-called augmented operator, which is the polynomial P plus, now of D plus 1 variables, which acts on the first D variables as the polynomial P, and the last variable is not considered at all. So this is a very nice representation. And now we can use this result of Bonnet and Tumansky. Our distributional kernel has P omega if and only if the augmented operator is surjective. And now we can use all the machinery of Malgrange, Hermander, and other mathematicians to study the surjectivity of this augmented operator, which is, of course, the case if X times R is P plus convex for supports and for singular supports. Okay, and with this, Bonnet and Tumansky showed that convex sets always have P omega because if X is convex, then X times R is also convex, and in convex sets, the operators, differential operators, are always surjective. I studied this problem for quite some time, and with the results that the kernel has P omega if P acts along a subspace and is elliptic there, if it is semi-elliptic and the zeros of the principal part is a one-dimensional subspace. This applies in particular to parabolic operators, or if the dimension D is equal to 2. So in this case, not only does the distributional kernel have P omega, but in this case, the augmented operator is surjective if and only if the operator is surjective on the space of smooth functions over X. I will skip this. And now with Andreas, we were able to show the following. So we are interested in the property omega for the smooth kernels. And if our differential operator is surjective on the smooth functions and the distributional kernel has P omega, then the smooth kernel has omega. And this allows to give the following examples of kernels with omega, because whenever the augmented operator is surjective, the operator P will be surjective on the space of smooth functions over X. So our previous theorem applies, and therefore the smooth kernel will have omega in the case when X is convex, no matter if P is hypoelliptic or not, if P acts along a subspace and is elliptic there, if P is a product of first order operators or a parabolic operator, and also whenever D is equal to 2. Okay, now we have property omega. We wanted to have omega with control. So given a compact set K, what can be said about the location of the compact set L, which appears in this property omega. And for this, we introduce the last notion of this talk. We say that a pair of compact sets K and L, where K is contained in L, is augmentedly p-locating for X. If the following holds, you choose an arbitrary interval in the closed bounded interval in the real line. And whenever the support of the augmented operator applied to a compactly supported distribution in X times R is contained in the Cartesian product of K with this interval, this should imply that the support of U is contained in L Cartesian product with this interval. And this should also hold this implication when you replace the support by the singular support. And the reason why this notion is interesting is the following proposition. So assume that our augmented operator is surjective, that we have two relatively compact open subsets X1 and X2 of X, X1 contained in X2, such that their closures are augmentedly p-locating. Then we have the following. We can choose an arbitrary open subset of X1, so the first one of our augmentedly p-locating pair, with a property that the closure of this X1 prime is contained in X1, and then for an arbitrary compact subset M of the large open set X, arbitrary orders of differentiation which enter into the semi-norms. We find some constants C and S such that we can approximate, this should be Y here, sorry. We can approximate our solution G to the homogeneous equation in Y on the closure of X1 prime by a solution to the same equation on the large space, and we can control the size of this solution on this arbitrarily chosen compact subset M of X in this way. So this is a generalization of this Salo-Hyland theorem. Of course, now it is now one has to study when such a pair is augmentedly p-locating, which of course depends on the polynomial p. However, if these sets are convex, then they are augmentedly p-locating for an arbitrary non-zero operator, which brings us to the first quantitative Runge approximation theorem. How much time do I have? 4 minutes, okay, thank you. Which reads as follows. So we have a convex set X, a subset open, a subset Y of X, two compact subsets K and L, of which K should be convex and contained in the interior of L. And then we have this quantitative Runge approximation on our compact set K up to an arbitrary order of partial derivatives. We can find for an arbitrary zero solution on the small set an approximating function which is a zero solution to the same equation on the large set, which can be controlled by the supremum norm of the function we want to approximate on L in this way. Okay, so for convex sets, we can show something for arbitrary operators. Now let's come to elliptic operators. We choose the same notation as in the Hyland-Salo theorem. Assume that Z is continuously an open subset with continuous boundary, relatively compact, whose closure is contained in X, such that X does not contain a bounded connected component of the complement of the closure of Z. Then for an arbitrary open subset Y, which contains this Z, and an arbitrary compact L contained in Y, such that the closure of Z is contained in the interior of L, we have this quantitative Runge approximation theorem. We can control the size of the approximating function H on an arbitrary compact subset K of the large set by this error threshold. Okay, so this is now a generalization of this Hyland-Salo Wykład-Zalow result for constant coefficient elliptic operators, which reads very similar to the original one. We also have a result for the wave operator in one spatial variable. Recall that this geometric property here, that for the small set y, there is no x in R2 for which the complement of y intersected with the diagonals translated by x. This is characterizing when the restriction map of the smooth solutions to the wave operator on R2 to the solutions on y has dense range. And now we have a condition on the larger compact set L in order that K and L are augmentedly p-locating for this operator, which reads as follows. Of course, we have to choose again K, a subset of the interior of L, and assume that it is not possible to find an X in R2 such that Y, our small set on which we want to approximate, the complement of L intersected with the diagonals shifted by X has a bounded connected component which is contained in a small set. And then we have again a quantitative Runge type approximation theorem. Okay, the last slide is concerned with parabolic operators and typical regions encountered in the study of parabolic operators. So regions in space-time where the time interval is the positive real axis for the small space, respectively the complete real axis for the large space. And we have open subsets in Rn for the space part of the space-time region. Z should be a continuously bounded open relatively compact subset of G1, such that G2 does not contain a bounded connected component of the complement of this closure. Okay, here we have an arbitrary compact time interval chosen in such a way that if we increase it a little bit by delta, we still have a subset of the positive real axis. And then we have, again, a quantitative Runge approximation theorem. Recall that these parabolic operators are hypoelliptic ones. So here we only need the supremum norms over compact sets without any derivative. This gives the topology, the compact open topology on the kernel. Okay, so this is all I wanted to show you. I will skip the sketch of the proof of this geometric theorem for time constraints, and I finish with a list of references. And since I'm already up with my time, I will not comment this. Thank you very much for your attention.
Any questions?
I have a question. Coming back to this condition omega, I guess it's important for this Wykład-Zalow result, and it comes from this result, this condition omega, right? I mean, the way you present this condition, it relies heavily on this Wykład-Zalow theorem. However, I am used to a different form of this condition. Are those conditions the same, really?
We did not study this yet. So the result of Wykład-Zalow
condition of omega by Fox, I guess. So are those the same conditions?
We don't know yet. So this result of Wykład-Zalow, let me go to this one here. This is proved by a so-called unique continuation inequality for solutions of uniformly elliptic second-order partial differential operators in the setting of Sobolev spaces. We have the impression that this is somehow related to the Vogt formulation of omega by the dual seminorms. So you have some multiplicative inequality, but we did not have the time to look into this. So So there is some hope, let's say, to use the tools of Rüland-Salo to prove property omega for variable coefficient, for the kernels of variable coefficient, elliptic operators. But the result is really technical, and we did not manage to study it in full detail up to now.
All right. Maybe a second question. How strong is this assumption that the matrix map should be symmetric? Is it like a crucial condition? Or
No. Okay. No, this is, I think this is just, without restriction, you can say that this should be symmetric. Of course, this W1 infinity is crucial, and the uniform ellipticity. Yeah.
Any other questions, remarks?
Do you know any version of Laplace theorem for spaces of smooth function on closed sets? For example, spaces of Whitney threads on closed sets.
I think there are versions in the sense that if you start with a solution on a closed set, whatever this may be, you want to approximate this solution given on a closed set by a solution to the same equation on a given open superset of this closed set. I think there are some results in this way. In the book by Narasimhan, complex manifolds and elliptic equation, I can look this up. Yeah, so if this is the direction you're thinking of, that the closed set is the one where your initial function is given, which you want to approximate, I think there are some results. But I think these closed sets, maybe they should satisfy the property that they coincide with the closure of the interior. So no singletons or fractals allowed. Only from the top of my head.
Any other questions, remarks? If not, then let's go once again.